I grew up bouncing around the U.S., Midwest, New Jersey. Um, went to college at Oberlin in Ohio, and then graduate school in Urbana, Illinois, and then Stanford. And then I've been a professor at Oregon State University, which is a kind of engineering and ag-oriented school, oceanography and things like that, natural resources in the state of Oregon. And I started working in AI in 1977 when I started graduate school. So at this point, I'm retired, but I've been working particularly in machine learning, since 1977, and along the way, I have done quite a lot of service work. I was president of the Machine Learning Society, president of the AI, something called the Association for the Advancement of Artificial Intelligence, which is got the AI Scientific Society. So I've been through a lot of meetings. So yeah, so I've touched a lot of different things in machine learning and applications. I suppose the starting in around 2000, well, actually late 1990s, I started working on machine learning and AI in problems in ecology, climate change, sustainability, conservation, wildfire management, things like this. Some of those involved things like computer vision. So trying to, classify insects or animals by species from their appearance, which is useful for all kinds of different things. But also trying to model how wildfire spreads and the effectiveness of different kinds of interventions to try to reduce the risk of catastrophic wildfire. And most recently, I've been working on problems in sensor networks. So, sensors have gotten cheaper and cheaper. So, your smartphone has several thermometers in it, right? And they cost just like fractions of a penny. And so it's possible now to make weather stations, for instance, that are, a factor of 10 or a factor of 100 cheaper than traditional weather stations that were from 20 years ago, because they can all be made into sort of a no moving parts package. And so I'm involved in some efforts to deploy such weather networks and then detect when sensors get dirty or break or whenever that they need a technician visit. So it's kind of, health maintenance for sensor networks, maybe. Yeah. So, and then I guess most recently, I've been interested in all the issues of trying to overcome the brittleness and lack of robustness of AI systems. So, machine learning systems are very good for data drawn from the same distribution that the training data came from, the same source, the same probabilities of different classes or categories, say, of objects. But they fail pretty badly when they encounter something new that they've never seen before. So I used to use as an example, imagine that you were training a self-driving car in Europe or the United States, and then you took it to Australia. What does it do the first time it sees a kangaroo? And I was just making up that example, but then Volvo did exactly that. And the computer vision system on the car failed because it couldn't figure out what kangaroos were and whether they were safe to drive through like a piece of newspaper blowing in the wind, or whether they were dangerous and the car should take evasive action. So so I'm interested in those kind of I guess the unknown unknowns problem for AI systems. Yeah, so the big challenge there was there's not much data available on wildfires, although that's changing now that we have better and better remote sensing of wildfires and drones and things like that, so we can map them much more accurately. So we worked with simulation. So there have been wildfire simulators developed for use in what's called tactical firefighting. So, you have your boots on the ground, you have firefighters in the forest or whatever. You have to decide where to deploy them, where you think the fire is going to move, stuff like that. And so there's a Forest Service lab in Missoula, Montana, that had developed wildfire simulators for that specific task. We combined that then. We were interested in the question of, are there things we can do today that will reduce the risk of wildfire over the next 100 years? So a completely different time scale. But we took their simulator, and then we also added a forest growth simulator, which was based on sort of how vegetation change over time in forests. And that had been developed by people interested in forest management, timber production, things like this. And then we needed a model of lightning strikes. Where does lightning strike in forests? Where a new fire is going to be most likely to be initiated, and then a model of fire duration. How long will a wildfire burn? And then if you combine all those, then we could predict how fuels will accumulate on the forest floor, where the fires will be ignited, and where they will spread to. And so then we had a sort of simulator so we could predict the behavior of fires over, say, a 100-year horizon. Then we could ask, okay, now suppose you have some things you might do. You might go in and do fuel reduction or create fire breaks, or those are the main things we explored. Was or you could change actually insurance liability laws for privately owned fire landscape to see what incentives would encourage landowners to reduce fire risk on their property. So we studied those things, and we use reinforcement learning primarily as the machine learning tool, because you've got to think of taking action every year, right? And you're trying to get the whole 100-year trajectory to have certain properties to it. So reinforcement learning is the right tool. So I haven't done any work in self-driving cars, so I'm sort of a spectator to that work. But of course, it's something that's very easy for audiences to relate to. So that's why I'm using it in my examples. I'm currently serving on a panel of the National Academy of Sciences that is we're preparing a report on machine learning and safety critical applications. And so I've been learning a lot. About half the people on the panel work on self-driving cars and associated problems. And it's really interesting to talk to people in safety engineering or reliability engineering, because they have a very different mindset, I think, from machine learning and AI people. In particular, in machine learning, we usually think about the error rates of our systems, or if we're like detecting the presence of a species or something, we look at, or a disease, we think about false alarms where we falsely detect the disease when it's not really there, or missed alarms where we fail to detect it when we should have, right? But they take a much more nuanced view of what the potential harms, they call it the harms that the system could have. So with a self-driving car, the obvious harms are, it could brake too suddenly or collide with something that would hurt the occupants of the car. It could strike property or people or animals in the external environment and hurt them. You could, obviously, we've seen more recently problems in San Francisco with self-driving cars just causing traffic jams by sort of having false alarms where they think something's wrong, and so they pull over to the side of the road, but in a crowded city situation, there is no side of the road, so they just pull over to the right-hand lane and stop, and it has created big traffic problems. And they've struck fire engines, and so they've also just not handled unusual situations with emergency vehicles. So anyway, these reliability engineers, they try to enumerate all the different things that could go wrong, all the different harms that the system could create, and then what's the probability that each of those will happen, which is a very hard thing to estimate, I think, for self-driving cars. Well, both of those steps are very hard for self-driving cars, because in reliability engineering, traditionally, the problems have been much more narrow, right? And so it's usually been possible to enumerate everything that could go wrong. And the big challenge with self-driving cars is we're relying on computer vision in an open world where new things can happen all the time. The system could see there could be some novel kind of vehicle, like I don't know what you call these things, these electrically powered kind of UNIS boards. I don't know what they're called, that have a fat wheel, and you just stand on top of them and or on the side of them. And anyway, people riding those behave differently from people riding bicycles, behave differently from pedestrians. And the self-driving car needs to predict the future location of everything in its environment, right? So that it can plan to avoid them all. And so that's the kind of novelty that can lead to harms, to collisions or other problems. So, but in any case, the reliability engineers, they try to estimate all of these things, the harms, their severity, and their probability, and then they multiply those together to get a notion of risk. And then they want to drive that risk down to 10 to the minus 8 or something, 10 to the minus 7, some incredibly small number. And they do that by designing multiple layers of mechanisms, right? So not just the AI components, but all kinds of other things. Better sensors, more sensors, sensor redundancy, redundant computing, redundant networking, and so on to try to control and mitigate risk. And I think this is a really interesting area where we need more engineers trained in both AI technology and in reliability engineering to think about building these kinds of high stakes AI applications. Well, I know another thing is if they lose network connectivity, they will also pull over, right? And this was a big problem. There was some sort of a large event. I don't know, it was a concert or a sporting event or something, where a whole bunch of the self-driving cars, I think from Cruise, all came to the same place, but there were so many people there that there was competition for the cellular telephone signal, the data signal, which the cars were also relying on. And so a lot of them pulled over and causing another traffic jam because they couldn't get network access. And I guess we've learned recently that the Cruise cars actually very frequently called for human help when they got into any kind of trouble. There were human operators, so it was a bit of a Wizard of Oz situation, right, where there were human controllers involved. It wasn't really full autonomy, and so they were desperate to have that network connectivity. And when they lost it, they were programmed just to pull over. Now, what should they be doing instead? Wow, that's a super hard question to answer, I think, right? I know that there was a really serious traffic accident that occurred here in near where I live, maybe 20 years ago. What happened was that there was a grass field where there was a fire happening, and it was right next to the interstate. And the smoke from the fire suddenly blew across the interstate and obscured the visibility of the cars. So drivers couldn't see what they were doing as they were driving along it. at 65 miles an hour and then entered a cloud of smoke. And so people hit their brakes, and then that caused a chain reaction of collisions, and I don't know, something like maybe 17 people died in the resulting fires because the cars caught on fire. Now, what should a self-driving car do in that case? Well, the drivers pulled over to the side to try to avoid the problem, but they still got struck from behind. The right thing to do would have been to just keep driving, right? Especially if we had radar, which would let them see through the smoke. But hitting the brakes or pulling over was exactly the wrong thing to do in that situation. So maybe, but in an awful lot of situations where there's something wrong, ice, traffic, an accident, you pulling over is exactly the right thing to do. So, in some cases, maybe there's not a single right answer, and even for human drivers, you can only tell after the fact what you should have done. But you can see some. I mean, there was a recent, probably the most recent failure, right? Was this case where a human-driven car struck a pedestrian, knocked her underneath a self-driving car. The self-driving car then tried to pull over to the side of the road because it knew something was wrong, and it dragged this woman about 20 feet, I think, or maybe 20 yards. Anyway, very bad problem. And that was a good example where the self-driving car didn't have sensors looking down under itself, so it didn't know that it was dragging this person. And I think, could a human driver have known this? Probably. They would have had a better model of what happened, the dynamics of the woman being thrown under the car. Maybe the human driver would have recognized it. Maybe if they were looking in the right direction at the moment that it happened. Maybe they would have felt that there was some resistance, additional, like the brake partly on, and they would have noticed that. But it seems like there's a failure, in some sense, a sensing failure in the self-driving car, that it wasn't able to detect the situation. So, a big challenge with novelty is you got to have sensors so that you could have a chance of detecting the novelty. And the sensors could either be physical sensors or kind of digital sensors, right? That you're computing the right quantities to know that something novel has happened. And then you need the right representation so that novel things look different from normal things, right? So, I mean, one of the most important things of deep learning is that it learns its own representations, right? The traditional way we build computer vision systems was we wrote our own code that would extract features from the image, because you can't work with the raw pixels. They're like, a single pixel at position 5, 10 doesn't mean anything. You move the camera slightly, it means something different, right? It doesn't have any absolute coordinate system. And so you need to extract features. And so people worked a lot on what would be good features to extract from images, and many decades of work on coding up cool features. And then we would take those features and put them into a machine learning algorithm. And so that was the state of computer vision, say around 2010, 2012, when deep learning came along and showed that if you have enough layers of deep network, the network could learn its own features. And that those would turn out to be much better features than the ones we were building by hand. And people got extremely excited about this. It led to much better performance, right? And that's really been a driving factor in everything, including things like GPT models. But a problem with the systems learning their own features is that those features are very much specific to the task the system has been trained on. So they're not good at recognizing what we call the out of distribution or the novel cases. Because if the world if the training data has not exhibited some axis of variation, I don't know if this is a very vague term, but suppose the system has only seen people that were 4 feet tall or shorter and never seen really tall people. It might not have a feature that can represent tall people. And so it will just because I think that this networks tend to learn features that are more like bins in a histogram, right? So it might have a bin for 1 foot, 2 foot, 3 foot, 4 foot high, but not for 5, 6, or 7. And so, when it's watching, say, people in the NBA, it's going to map them into the because that's the tallest size it has, and they won't look unusual to it as a result. We see this happening a lot in the animal recognition stuff that I work on. And so this is we need to do some, I don't know, feature engineering or synthetic data construction or something, so that the network has a representation for things beyond what was in the training data, not just what was in the training data. Then it can detect that something's outside its training data, and then it can at least raise an alarm and say, this is something new, I need help figuring out what to do. Well, there's a good question. Yeah, I mean, I think that they shouldn't have been allowed on the roads in San Francisco. Now, Waymo seems to have been doing much better, right? And they've been involved in a lot fewer incidents than the Cruise cars were. And Cruise has been, banned from California, at least temporarily. So it could be, it's important to point out that none of these systems are based purely on machine learning and computer vision. There's a huge amount of safety engineering, lots and lots of manual things going on in these systems. So maybe they have just, they do. I know the Waymo does extremely detailed mapping of all the streets and intersections and so on. So I think they have much better models of environment, perhaps. They've certainly done more testing in the real world and much more testing in simulation, I think, than any other of the vendors. But the question, these corner cases, they're just in an open world. They're always going to be novel situations, and the challenge is to be able to detect the novelty and then to figure out what to do in the presence of the novelty. Because we talk about what we call nuisance novelty, which is, there's something new I've never seen before, but it's like on the side of the road and it doesn't matter. But it could be something that it's a new kind of vehicle that's going to pull in front of me, and even though it's on the side of the road, I need to realize that I need to take evasive action. So it's just super difficult. So I think it's I'm not optimistic that we can have full autonomy in arbitrary environments. What seems to maybe be more possible is to define a kind of envelope of cases, dry days, no fog, and sort of low density of vehicles in a known place where we can achieve the desired levels of safety. So people talk about maybe self-driving semi-trucks on the freeways and the interstates outside of cities under good weather conditions. I can believe that we could probably make that work. So then the challenge is just a system that can correctly tell whether it's inside the safety envelope or outside of it. And if it's outside, then a human driver has to take over instead of the autonomy. So maybe we could do something like that, a partial solution where we restrain the system to just particular operating conditions. But I think, for instance, particularly Tesla has been completely irresponsible about basically beta testing on their customers stuff that is really not and giving it a name like autopilot or full self-driving when it is not nearly at the level of autonomy that should qualify to have named that. And I think people have been pretty tolerant to the fact that a lot of there have been people killed in Teslas, but it's mostly Tesla drivers, and people I think are more accepting of that, saying, well, they're kind of idiots to trust it. But when they start killing people outside the vehicle, that's I think regulators should not allow this to happen. And the president's most recent executive order requires safety testing before deployment, and requires that the results of safety testing be disclosed to the government. And I think that, we need something like that. It goes against the tradition in the auto industry has been that you can sell something, but then you have to be monitoring for problems, and then they'll issue a recall if there's a safety problem, right? Which is completely different from medical devices where you have to prove that they're safe before you can sell them. And but I think the risks with self-driving vehicles are so high that we can't rely on the recall model. We need to switch to a regulatory model that requires safety testing in advance. It's a big research question. So if it depends a lot on how broad the task is. If we have a really narrow task, like let's say we're just trying to detect cancerous and precancerous cells in pap smears or cancer biopsies or something like that, skin cancer. Our technology, I think, is getting to the point where we can reliably have a system that knows its own limitations. It has what I call a competence model. So given a new image, it can say, this is outside my training data. I can't give you a good answer. Or equivalently, it can say the probability I'm right is less than 0.1 or whatever, just don't trust me. When we move to self-driving cars, we have a broader set of concerns, because we have this question of accurately predicting the behavior of everybody, all the other things that might be moving in the environment, the other drivers, pedestrians, and so on. And a big issue there is, we'll come back to that later. Anyway, but then when you go to large language models, you can ask them anything. So the scope, it's something that we should have anticipated in advance, that the broader the scope of an AI system, the harder it's going to be to test it. Because you need a test set now that's kind of the same size as the training data, which is already, billions and billions of documents. In fact, we're using all of our documents for training right now, so we don't have hardly anything left over for testing. So, and it's not clear that you can even test, like, in safety engineering, you have to be able to say that the probability of error is, say, less than 1 in a million. Well, I don't know if you had any statistics yet, but when you're trying to estimate a probability that's like 1 in a million, you need something like 10 million data points to estimate that low probability, right? So you need a ton of testing, and we just don't know how to do that for large language models. I think in contrast, when we write traditional software, right, we're usually thinking very systematically when we write code, right? I mean, you have the so-called basic blocks in a program that don't have any conditionals in them, and then you have if statements and while loops and all that stuff around them. But each basic block is just a series of instructions, and it's designed to take any set of input variables that have passed all of the sanity checks, and then do the same thing to all of them, right? So it's very systematic, and we can test that code. We test code with test cases, right? If you write good tests, you get test cases there, and we can be pretty confident if the basic block handles a test case correctly, it will handle all other test cases for that same basic block the same way, right? And so that leads to this notion of test coverage, right? Which is that you want to have test cases so you've exercised every branch of every conditional in your whole program, and that gives us some sort of confidence that the program is working properly. With machine learning, the system is built just by having just individual points, right? So we give it a whole bunch of training examples, and we're hoping that the system finds some systematic way of generalizing from them. But the only way we have of testing is, again, to probe at individual test points. But now we can't be confident that because the model is right at individual points, that it's right everywhere in between them, in some sense, right? And so this is the fundamental problem of testing. We don't have good ways of testing for systematic good behavior in machine learning models. So I think that we might be able to do that. And for small networks, there have been some techniques developed, but nothing is practical yet. Well, they've tried. I mean, they've brought in human red teams, uh, and they certainly have tons of kind of metrics that they measure. But I think that that it's that I mean the models still make things up with the probability, right? So um, I know there's a recent paper that just came out that tries to measure the hallucination rate of these models, and I don't remember exactly. My recollection was something like 3% of the queries in their test cases were led to hallucinating answers from ChatGPT. And I think Bard had a much higher rate, like 8% or something. Um, I think in general, when you ask them questions outside their training data, they don't have a model of their own competence, so they always generate an answer, and and that's when they get into trouble, I think. Um, so we can figure out how to build competence models for large language models, um, and and that does require somehow saying, well, is this is this within the envelope of my training data, and how to do that at that scale and with that breadth. We don't know how to do it. It's much easier with yes no questions, multiple choice type problems, but when you're generating over tens of thousands of potential tokens and sequences of thousands of tokens, that's a gigantic space. How do you test that, the correctness of the answer? The kinds of questions you ask ChatGPT have multiple valid answers, dozens or hundreds of valid answers. And so it's very hard to score them on correctness. That's why they use this reinforcement learning kind of strategy instead. So no, I don't think anybody knows how to test large language models from a safety standpoint. We're trying, but but the basic science is missing. There are some people who advocate so-called end-to-end training, where you use reinforcement learning that takes an image or recent several frames of video as input, and then decides how to actuate the robot's motors to do things. And certainly there are some robotics projects that have done that, but reinforcement learning is incredibly data hungry, and usually you wear out the robot before you get enough training data to get to good performance. So it's much more common now to use really high quality simulators and do what's called sim to real transfer. So you train on billions of examples of simulation, and then you try to transfer that to the real robot. And it surprisingly works pretty well. And you do it by doing what they call domain randomization, where you design the simulation so that the robot that's being controlled in the simulation is not always the same robot, but you vary its parameters a lot so that the system learns to be robust to the exact length of the arms, the strengths of the motors, and stuff like that, so that when it moves to the real world, where the real world isn't exactly the same as the simulation, it still can perform well. So people try to do that end to end, but I don't know of anybody that would try to do that for something as complicated as self-driving cars, because they're predicting the dynamics of the world is a huge challenge, right? It's not just applying Newton's laws and saying, well, everything that's moving will continue moving and so on, because you've got people making decisions in real time, like when you're making a left turn, and on a road, what's the probability that one of those oncoming cars, instead of going straight, turns and smashes into you, like deliberately? Oh, it's very unlikely, right? But that's a kind of a social agreement that we don't want to kill each other, and so the driver of the oncoming car is going to avoid you. But it's not physically impossible. They could do that, right, at any moment. And so so learning the dynamics of the world is also learning about our social conventions for cooperation, and estimating, I guess with a bicyclist, you're going to have a higher probability they might blow right through a stop sign. With a pedestrian, they might jaywalk at any point along the side of the road, not just stick to the crosswalk. So you need to have a sort of uncertainty, cloud around each object and agent in the world, and then you got the car has to plan its trajectory to stay outside of those uncertainty clouds, and so it's really hard to learn those kind of complicated dynamics in an end-to-end fashion. Instead, it's done with lots of individual trajectory prediction problems, traffic prediction problems, the behavior of cars under different, in bumper to bumper versus high speed open road, and so on and so forth. They have models for all of those cases. And then they can do something that looks a lot more like planning, which is to say, okay, current state, where do I project all of these things to be in the next, 50 to 200 milliseconds, and then what actions should I take as a result? So it's much more of an engineered solution. And now, of course, to test it, you're testing a mix of machine learned code and hand coded, and you want to have unit tests and then system level tests and all those kinds of things. But how could you prove that it was correct? This is a totally open question. That is a challenge. So one idea has been to so-called adversarial testing, right? So imagine this self-driving car has a certain, it's all coded up and it's running, at least in simulation. Now in simulation, I could say, well, suppose I put an adversary in charge of a pedestrian. What is the worst thing a pedestrian could do that would cause the most damage, right? And you can ask about that. That turns out to be ridiculous because it has things like basically suicidal pedestrians that just run in front of the car, straight toward the car, things like this. And they're just extremely unrealistic. I mean, they're not impossible, but you're not really wanting to design for that, right? So you have to think about kind of a constrained adversary where you think about, okay, within some range of behaviors, like let's think of what's the worst thing the pedestrian could do in that range. But the hope is that you can then, that involves now solving an optimization problem to try to optimize the pedestrian to do the most damage, and that can be quite challenging in itself. But assuming you can do that, and the car can, if you can, depending on how much freedom you give your adversary, that gives you a measure of how robust you are to errors in your pedestrian model, right? So people try to do that, but I think it requires a certain amount maybe of human creativity too. I've known of some cases where people have hired script writers from Hollywood to imagine all kinds of wild scenarios, right? Just to try to generate things. And now with generative AI, maybe we can also use some of our AI tools themselves to help us imagine novel and crazy situations. So, but yeah, I think, that they're out of all the unknown unknowns. They're the ones where we won't even have the right sensors to detect that they're happening. The ones where we have the right sensors, but we're missing the representations inside the computer. So sort of the software isn't up to snuff. And then there's the ones where we have both the sensors and the detection, and then we should be able to handle them. And the goal would be to increase the size of the coverage of the things we can handle. But I mean, there are all kinds of trade-offs, right? We can put down-facing cameras underneath the car and things like this, but it will cost money and more computer power in the car to look at more sensors. So, I mean, in Tesla, Musk has said he only wants to use computer vision. Well, he's going to have a lot of trouble in bad weather conditions. That's the reason people put radar on cars, is because it can see things that computer vision can't see. But it costs more, and same with LiDAR. So, this is where regulation probably has to come in and say you have to have these detection capabilities at a minimum. And if you do have these, then maybe your liability insurance is going to be cheaper. If you can demonstrate safety, then the insurance companies will not charge you so much. It will be financially feasible to own and drive one of these cars.